So, welcome back here. Welcome, Elmar. After Jan Jürgens, we now have Elmar Jürgens. Don't mix them up. Hello.
Hi,
Where are you located in which city, Elmar? Today.
in Munich. And I
In Munich.
actually
So,
happen to share an office and an email address
so you are very close to us in Munich. Yes.
space with Jan in the
Yeah.
university in Munich, and listen because it was only one letter difference.
Oh, that's very tricky. Yeah. And you're an expert on testing, and you have your company CQSE GmbH, and you started with testing with, or you have experience, have had experience since you worked on your PhD thesis on static code analysis, and now you're talking to us and giving us some insights on why you should avoid or how you can avoid the too many tests which are unnecessary, and do the right tests and do them more efficiently. And I'm really looking forward to this talk on test intelligence for architects. So the stage is yours.
Reinhard, thanks a lot for the introduction. My audio just dropped out for a while. Just to make sure, can you hear me? Maybe Reinhard can give me a signal, or Lisa? Perfect. So let me start. Very many of the teams we work with are faced with the challenge that the software they architect and their test architecture must support quality assurance for more and more functionality in less and less time. More and more functionality because typically we have to build in more and more features. We are hardly ever allowed to remove functionality from our system. And paradoxically, we don't get more time for quality assurance of more features because release cycles are getting shorter and shorter. And I think this ties nicely into the keynote topic Uwe presented today, where he made a point that our environment and economies get more volatile and more uncertain. And the typical reaction is to get shorter release cycles, to have quicker feedback if our hypotheses are correct or not. And 20 years ago, when I started being involved in developing and architecture decisions, the typical reaction for this was to simply retest everything, either via manual tests and more frequently via automated tests. And in my experience, this is not an applicable approach for many companies anymore. So today, I want to talk about analyses that help us be more effective and more efficient in our testing efforts, to add to your toolbox as architects. And the key idea I want to present is how to get transparency into the black box of software testing. And I want to start with a metaphor that you all know what I mean with this. X-ray pictures. This is an X-ray picture of a knee, of a kneecap, more specifically, of my right kneecap, which I unfortunately broke a couple of years ago in an accident. And the bright wires you see here is the steel that holds together the pieces of bone of the kneecap. And those wiggly things are the clamps that close the scar. Why do I have that here? Because it felt to me like a very specific, very effective approach to quality assurance. Now, what do I mean by that? Obviously, the accident and the emergency surgery on the same day didn't feel structured at all. But 2 weeks later, you have to go to the doctor again. And basically, the goal of that visit is quality assurance. And what I found interesting was that he did not ask me where my pain was. He didn't take a blood sample. He didn't take my temperature. He only took this X-ray picture to see whether the changes performed by the surgeon had resulted in a picture he was expecting and was fine with. So instead of retesting everything he could with me as a patient, he did a very specific quality assurance measure. And leaving this metaphor behind, what I want to talk about today is how we can use the data from our own development and test processes to get a similar level of transparency about what we changed and about how the result is, and where our quality assurance measures, namely tests, have already inspected the changes that were performed to the system. And before I start, I want to give you some background on who I am so that you know where the experiences I share in this presentation come from. I look at this topic from two roles. I studied computer science and did my PhD in software quality analysis in this area, and finished that in 2011. And then I co-founded a company called CQSE, which builds those analyses and uses them in practice. So, and I worked at the Technical University of Munich for 10 years after my PhD as a postdoc, and I still supervise PhD students. So I look at this topic from two perspectives. The first perspective as a researcher. In this perspective, I'm interested in what is really relevant to measure, because unfortunately in software quality analysis, we often measure what is easy to measure, not necessarily what is relevant to know. And in the practitioner perspective, I'm interested in impact, because just because there's some research, nothing improves. Just because you have some tool that runs at night, you don't necessarily find more bugs with less effort. So today I want to talk about what is relevant to measure and which analyses really help, and how can they be employed to have impact in practice. Last slide on background. This is some of the companies we work for. And the key message I want to send is that the approaches I present today are not limited to a specific domain, programming language, or organization style. Because while at first glance, a business information system written in Java looks very different from an embedded system written in C, if you take a step back, the same challenge exists, that we have to test more and more functionality and less time in all those domains. So enough on background. Before I start with the analyses, I want to get us all on the same page regarding the data that we use for these analyses. And I primarily work with three data sources. The first one is version history, the code, all the changes that were made to that code base during the history of the system, and all the branches. And I take it you are familiar with that. The second data source is tickets. And by that, I mean everything that's in a ticket management system like Jira or Azure DevOps, like bug reports, change requests, features, epics, user stories, and so on. And I also take it you're familiar with that. And the third data source is test coverage. And I want to talk about that and get us all on the same page, because my experience is that while many of us work with test coverage, there are some aspects of test coverage which are important to these analyses that are not so widespread. And what do I mean by this? This is an example from a Java open source system called Pixelitor, an open source paint program. And how we typically see test coverage being employed in practice is like this. You run your unit tests in CI, measure test coverage, and then use it to inspect which parts of the code were not tested, and do I maybe need a test for that? Excuse me. So in this picture, everything that was covered by the tests is depicted in a green background, and what was not executed is depicted in red. And the typical use case for test coverage is to look at this as a developer and then think, do I maybe need a test case that runs into this if? Today, I want to present, or I want to highlight two other features of test coverage. And for that, I want to zoom out a bit. This is the application I use to showcase, the Pixelitor. And this is its code base, visualized as a so-called tree map. And the basic idea of a tree map is that we use rectangles to represent components of the software system. And the bigger the component lines of code, the bigger the corresponding rectangle in surface area. So this is the Java packages of the Pixelitor. This is its classes, and these are its methods. And it still holds the bigger a rectangle, the bigger the corresponding method in lines of code. And what we can now do is use these tree maps to visualize coverage. As in this picture, now gray means not covered during testing, and green means covered during testing. And this, for example, is the coverage of the unit test suite of the Pixelitor application. Now, the 2 points I want to make are these. The first one is that from the point of view of the coverage profiler, it's not important if we observe an automated unit test, an automated end-to-end test, or a manual test even. And to drive this home, we made this time-lapse video where we have the code on the right-hand side and the application on the left-hand side. And we start it up and we do a manual test. And on the right-hand side, you see the code that it gets executed exactly at the moment where the execution on the left side happens. So important thing is we can use a coverage profiler to measure all the test activities that are performed in a system. I stress that so much because typically we see test coverage only being used for automated unit tests, but it makes sense to also use it to measure automated integration tests, end-to-end tests, or even manual tests. And the second point I want to make is that we can use it to measure the coverage of individual test cases. And in this example, this is the coverage of the test case, test Gaussian blur, which is one of the more important features of this application. And we can do that to measure the coverage of every single individual test case in a test suite. And then we can use this test case specific coverage data as a data source for some of the analyses I want to present. So this concludes the background. Now let's dive into the analyses. And the first problem I want to tackle is what to do if we have too many tests to execute all of them. And we've been working on this topic for 10 years, and there's a research body that spans several decades. And in my experience, more and more teams are facing this challenge because fortunately, many more teams have automated their tests in the last decade, but are now unfortunately faced with the challenge that it takes too long to execute all those test cases. We work with teams that have 80,000 test cases, and it takes them hundreds of hours to execute all of them. And often they are not easy to parallelize for different reasons. Sometimes because they involve hardware, which is expensive to parallelize, or they use other systems they interact with, and they can't be parallelized trivially either. And the key idea to still get rapid feedback despite slow running tests is to select a subset of those tests and execute this subset that's quick more frequently than the entire set of tests. And I want to present two approaches on how to select a subset that finds a large part of the bugs in a small part of the time that it would take to execute the entire test suite. And the first approach I present exploits redundancy between test cases. And our experience is that especially in historically grown test suites, there's a lot of redundancy between test cases, and we can exploit that so that we can select the tests in a smart way, so that even if we only invest a small amount of time, we can still find a large amount of the bugs. And I want to make this more tangible using the Pixelitor as an example. And what I want to now do is execute the test suite of the Pixelitor and the default sequence it gets executed when we run it. And the first test case in this test suite is the test Gaussian blur. And what I want to now do is build up test coverage, and every method that gets tested by this test case that has not been tested before this in this test run is depicted in green. And every method that gets executed but was tested before gets depicted in blue. Because this is the first test case in our test suite, everything it covers is green. The second test in the suite is called test motion blur. You see, it adds some new coverage here in green, but there's a lot of blue code, which is code that was executed by the test Gaussian blur before and is also executed by the motion blur. Third test case in this suite is called test lens blur. and the fourth one is smart blur. And you see there's less and less newly tested code in green and more blue code. And if we take a step back, we get this picture. This is the same tree maps, just smaller. And to the right, you see all the green code it covered. So we see that the additional code coverage we add with every additional test case gets less and less. And this is a typical phenomenon we see. Often in test suites, we see clusters of similar tests which exhibit this functionality. And for most of the coverage that they share, they either all find a new bug or none of them finds a new bug. So it's really only useful to execute one of them if we only have a little bit of time. And this is a toy example, but this is an example from a real customer project where it takes 48 hours to execute all the test cases. And this is a system that's embedded and runs on a medical device. And to the right-hand side, you see the time it takes to execute the test suite. And on this axis, you see the relative coverage, 100% meaning the coverage that the entire test suite creates. And you see these plateaus in the graph, which are the clusters. So when we jump to a new cluster, we create a lot of new code coverage. But as long as we stay in a cluster, we can still find new bugs, but only limited to that functionality. So the key idea to optimize that is to change the sequence of those tests in such a way that we produce a lot of code coverage in a very short time. And there's a lot of research on that. And the best approach we found, both in the literature and in our manifold experiments, is one that always takes that test case next, that per second of test execution covers the most untested lines. And if we apply that to the pixeliter again, the first test it selects is called test create and modify selection. So new test run, everything green. The second test is called test change view setting. And you see it does have some blue stuff, which is to be expected because if we run end-to-end tests, there's some functionality that gets executed by every single test, but there's still a lot of green functionality. And test change view settings sounds very different than create and modify selection. It's not blur, 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 but it hints at very different functionality. Third one is test second layer. Fourth one is test save image. Again, different names. And if we take a step back and use the same visualization, we see that it produces dramatically more code coverage in the same amount of time. Now, if we go from the toy example of pixeliter back to the real-world example of the medical system, if we use this heuristic, it transforms this picture into this picture. Same tests, same complete test duration. But if we now cut, for example, at 8% of the runtime, in this optimized ordering, we create more than 99% of the code coverage. And if we only invested 8% of the time in the original ordering, we would be below 20%. And the key idea behind is that if we now only run those tests, we have a much higher likelihood to find many bugs than if we only ran the beginning, the first part of these tests in the same amount of time. And this only is true if code coverage is actually a good approximation of fault-finding capability. And to find that out, we did a lot of empirical research to answer the question, which percentage of the bugs do we find if we only invest a little bit of the time? And for that, we used very many different approaches to get bugs. In two buckets. The first one is we looked at very many open source projects and looked into the history to find failing unit tests and then see would the optimized version also find that. This has the advantage that it's real-world bugs, but it has the disadvantage that it's not so many because typically you don't check in breaking changes that break your unit tests. You can find them, but you find a couple of hundred with hundreds of hours of work. So the second approach we used is to use mutation testing, where we automatically introduced known bugs into software systems. This has the advantage that you can produce thousands or tens of thousands of bugs, and for every single one, run the entire test suite to see if it finds it, and then run the optimized one to see if it still finds it. Many more data points, disadvantage of being less representative for real-world bugs. But both approaches together kind of balance out their weaknesses. And in our case, they produced very similar results, so we are positive that they hold. And in our experiments, we saw that in 6% of the time it takes to execute the entire test suite, we find 80% of the bugs that the entire test suite finds, only by using a different sequence. Or if we invest 11% of the time, we find 90% of the bugs that the entire test suite finds. And I have two showcases how teams use that in practice to help you get a better feeling for when this is applicable. The first one is Bayerische Versorgungskammer. They have a Java system that has a lot of automated end-to-end tests, and they run. You can run all of them in less than 24 hours, but it's still slow if you get the feedback the next day. If I break something and my tests immediately tell me, it's much easier for me to pinpoint what I did that broke the tests than if I get it tomorrow or maybe next week. Because A, I've forgotten some things, and B, I've done a lot more that could be the reason for breaking the tests. And what we did with them was compute a Pareto optimization, like the optimized ordering of the tests, and provide 1 hour of test budget. So every 2 hours during the day, they run this 1 hour of tests. And then at night, they still do the rerun all. And this provides a nice test bed to see how well this really works. Because all the bugs we don't find during the day with the optimized version, that only has 5% of the test budget, we find those bugs that slip through at night. And here we saw over the last year that with 5% of the test time budget, we find 70% of the failing commits. So for 70% of the problems, developers get feedback quickly, and the remaining 30% are still reported the next day. The second showcase I have is from a customer that builds tools, and they have their system is in C, and they have more than 140 hours it takes to execute a big system test, and it's hard to parallelize because the machines are so expensive that run that software. And what they use this analysis for is to optimize a quality gate before this expensive test run can be done. Because if there's a bug in the software that makes many test cases fail, this single bug ruins the entire test run. Because if you have 10,000 test cases and 1,000 of them fail for a single bug, you don't notice the other bug that maybe makes 2 or 3 test cases fail. So they have an acceptance test suite that must be passed before the expensive test run can be entered. And this acceptance test suite has 1 hour of more than 140 hours of the entire test run. And we evaluated that against historic bugs that were of this category from the last 2 years. And that was a full list of 31 bugs that had been found in the last 2 years on the big run. And if you only run the first hour in the default order, you find 4 of those 31 bugs. As a comparison, if you run randomly selected ones, you find 2. In the acceptance test suite they had built by experts, you find 8, and our optimized version finds 16. So I think this is a good showcase that in complex system, there's just so much data and so much going on that even as an expert in the system who's been with that system for a lot of time, you can't outperform the algorithms that have the data and can optimize for that. So taking a step back, we saw that only by exploiting the redundancy in the historically grown test suites, we can already squeeze out a lot of time and select a subset that quickly finds a lot of the bugs. What I want to now talk about is how we can improve that by adding another data source, namely the version history. And the idea is very simple. If we know which test runs through which code, imagine we executed all the tests yesterday, then most of the tests cannot find a new bug today because they don't run through code that was changed. So the key idea is, let's add changes to this analysis to see how much more we can speed things up. And to show you why this works, I have another example, this time from our own software system. We build a software analysis tool that has static analysis and dynamic analysis in there. This is our code base. Every small rectangle is a Java method. This is our backend, roughly 1 million lines of Java code. And the changes you see here were for a ticket that we implemented when Java released a new language version that contained the keyword closures, among other things. So whenever a programming language has a new version, we have to adapt. We have to adapt our lexes and parsers so that we can still process programs in the new version. And red means new code. Orange means modified code. And what I now do in a time lapse is run all our automated tests. We run 30 tests per second. All the methods that are executed by tests are flashed in white in one frame and then fade to green. And I want to make 2 points here. The first one is, if we have test-specific coverage data, there's simply a lot of data that these analyses can exploit. And the second one is, if something gets tested, it first gets flashed white and then fades to green. So anything that's gray or colored was not tested. I stopped the video now because I think the point got across. But what you see here is that most of the stuff we changed has not been executed by the tests. And I mean, this is just a subset of our tests. But back at the time when we implemented that change, we had roughly 5,000 automated tests. And only 4 of them ran through the changes. Not 4,000, 4. And this actually shouldn't come as a surprise, because years ago when we wrote those tests, nobody thought, oh, if Java gets closures, let's already write tests for them. That's not how it works. But all those tests, if they don't run through the code changes, they cannot find the bug that was introduced by this code change. So from a test optimization perspective, this is great because we can leave out all those tests that don't run through changed code. And the basic idea of test impact analysis is to exploit this. So in the first step, we throw out all those impacted tests. If we are lucky, this squeezes down the number of tests significantly. If we are not lucky, it's not enough, because this was unit tests. You see, most of them are very isolated and local. The next animation is of our end-to-end Selenium tests that run through our UI. Here you see a lot of the code is executed by most of the tests. If you focus on the middle here, for example, this code is executed by most of the tests. But if we run a test selection approach and change on a change code that gets executed by most of the tests, it still selects all those tests. So it doesn't speed up a lot. So as a second step, we do the same ordering I presented before. And this turns this picture where, if we run that some fail, into a picture where the same failures are moved more to the front. So first we select and then we reorder based on the changes. We did the same experiments, and we found that if we add the change information, we find 80% of the bugs that the entire test suite finds in 1% of the time it takes to execute the entire test suite, and 90% of the bugs in 2% of the time. And for example, we introduced this analysis together with Dolby, who have the challenge in their tests that they run through a large parameter space. for example, for bitrate. And they want their continuous integration to have less than 10 minutes for tests. And since they introduced this approach, they arrive at squeezing those tests into those 10 minutes, even though the number of test cases increased by more than 50%. So how do those two approaches compare? In my experience, they're both valid on a cost-benefit scale. Pareto optimization is not as good in terms of optimization as test impact analysis, but it's also a lot cheaper. For test impact analysis, we have to select and sort those tests on the fly based on the changes when those test runs are supposed to happen. For Pareto optimization, we can do, which is a lot of effort. And for Pareto optimization, it's sufficient if we do that every quarter of a year or something, and then compute a static list that we simply execute during test. And depending on your test process, on your test setup, on your architecture, on how hard it is to get test case specific coverage, we find in some situations Pareto optimization is the right answer. In some situations, test impact analysis is the right answer. So it's simply two different tools in the toolbox. The next analysis I want to talk about is what about those cases where we don't have tests for yet? Because we know through change coverage what was executed by tests, and we know from the version system what changed. So we can put that information together to find untested changes. Because there's a lot of empirical research that shows that for long-lived software systems, most of the bugs are in those areas that changed since the last release. And it also matches our gut feelings that if we change something, we should test it because there's a higher likelihood of bugs than in the stuff we didn't change for years and which has been tested a lot of times already. So how does that look in practice? This is an example from a business information system written in C#, 30 people working on it. Gray means, again, tree map, white are components, and black are files in that system. Gray means not changed since the last release. Red and orange means new and modified code. This was pre-agile transformation. At that point, they released 2 times a year. So 30, and this picture was taken before the release. 30 people had been working for 6 months to produce these changes. And obviously, a lot more changed on the right-hand side than on the left-hand side. So we should especially be careful to test this. This is the test coverage of that for that system prior to release. Aggregated of all test stages. Gray means not executed during test. Green means executed during test. And this is aggregated manual tests, automated unit tests, automated end-to-end tests, everything. So how does this combine? Now this picture shows test gaps. And gray means unchanged, independent of whether it was tested or not, because we know the gray stuff, since the code didn't change in a long time, we expect much less bugs here. The colored bits are the new and modified code, and only if it's green was it ever executed during testing. And the key idea of these test gap tree maps is to reveal untested changes. And what do the colors mean? Green means we executed this during testing. Could be that we found all the bugs, could be that the bugs are still in there. We know that testing can never prove the absence of bugs. So we don't really know how much we found in here. But the red and orange stuff is trivial to interpret. We can't have found a single bug in there because we didn't execute it ever during our testing efforts. And if you look here, there's entire components that were forgotten during testing. And in this situation, this picture was the day before the planned release, and the team decided not to release it like that. It could be that it's not a problem. Maybe it's functionality that we don't need now. Maybe it's functionality we don't need until May, and we know there's another 5 releases until May. So our goal with test gap analysis is not to get everything green as a purpose in itself, but it's to allow a conscious decision for the teams whether they want to ship it like this or not. And this team decided not to ship like this, but to postpone the release and do additional testing. Coming back to the analysis, this picture of the entire system is only relevant to those roles that are responsible for the entire testing efforts. In a lot of cases, if I'm working on a single feature or testing a specific area, the scope is too big. I'm only interested in what I'm currently working on. So what we like to do is add the third data source of tickets and then look at the test gaps through the scope of individual tickets. This is a screenshot from our own development where we use this analysis. And since whenever we commit a change set, we reference the ticket we're working on, we can crawl the version history and gather all the methods that were modified during the implementation of a ticket, and then compute the test gap for those methods. This is an example where you only see those methods that were modified during the implementation of this ticket. And our definition of none comprises that a feature branch can only be merged if it contains no non-trivial test gaps anymore. Dangerous word, non-trivial. But if it's like a getter that only reads a variable, a setter that only writes a variable, or a default constructor that only initializes variables, then it's fine if you don't write an automated test for that. We say this code is so trivial that we see that it works or not. And we even have research to back it up, where one of our PhD students did inverse defect prediction and showed that for such simple code, the defect density is way lower per line of code than for all other areas. So I think it's fine there, but everything else has to be tested, otherwise you can't merge it. Another example from a customer that uses it, in this case from the automotive domain. And here they are under regulatory pressure to have a unit test coverage, a very high unit test coverage on the low-level tests. So they're not so interested in that. But they use that to analyze the coverage of higher level tests, for example, for highway tests, to see if the new features are actually tested by the highway drivers. Or if they use it on a platform across different car variants, if specific functionality was tested in specific cars and matches the expectation. Now to the last analysis. I want to spend the last minutes on what we can learn from the past, more specifically from the bug history of our own system. And this combines all the data sources on the picture. This tree map shows the code base of an industrial software system. And every rectangle is a file. It still holds that the size of the file corresponds with the length in lines of code. And now on the color dimension, we have number of bug fixes in the last 3 years. And for this, we analyzed all the bug tickets. In this system, the tickets in the ticket system were categorized into bug, refactoring, new feature, and so on. And for this, we looked at the bug tickets, and then for the last 3 years, counted how often the file was touched during the fix of a bug. So this is a good approximation of how many bugs a file did contain. And if you look at that, you see that there were some bug fixes all over the system, but it's interesting that this block in the middle is way darker than the rest. Obviously, way more bugs were fixed here than in the rest of the system. This is a test coverage tree map for the same system. And the shade of green indicates how high the line coverage for that system is from the automated tests. And you already see the same pattern. If we superimpose them, then it becomes obvious that the area in the system that contains the most bugs does have a very low test coverage. So when we had this picture, we went to the team and confronted them and asked them, what's going on here? What's this code? And we learned that this is the front-end code in JavaScript. And this to the left and this to the right is the back-end code in Java. And it turned out that it was rather easy to write unit tests and other automated tests for the backend code, because long ago somebody had made the effort to set up a test framework where that was easy to set up. On the other hand, it was very hard to write automated tests for the front-end code. And whenever anybody thought, oh, let's write the unit test or another automated test for the front-end code, they noticed, oh, there's so much groundwork I have to do. It doesn't fit into the time I have available right now. Let's do that at some later point. And the consequence was that there were few automated tests for the UI, and that the bugs slipped through and had to be reported by the users. But when we confronted the team with that, they obviously decided to invest into the groundwork for the automated tests, also for the UI, and then closed that fundamental process issue. And when we looked at that system years later, the picture had changed. There was a lot of coverage here as well, and the density had changed as well. So I include this analysis because it's a rather simple analysis. It's a single-shot analysis. I don't think this makes sense on a continuous level. The other analyses I showed, test gap analysis, test impact analysis, they make sense to always run. This one makes sense to do a single shot to see, is there any surprising pattern you see in the tree map? And I stress that so much because it's such a simple analysis. You have all the data in the version control system and the ticket system. You just have to extract that. It's not a lot of effort compared to other analyses or other types of quality improvement measures you can do. That concludes my talk. I outlined 3 analyses that use data from your own test and development process to help you select the tests that find bugs most quickly now, reveal untested changes where new tests maybe need to be written, or reveal where especially high defect densities were in the past that could point at problems in the underlying development process. If you want to dive more deeply into this, we have online workshops that are free to participate where we dive more deeply into these analyses and take 90 minutes for that. And through these links, you can find a recording for the test gap analysis workshop we did last month, and also a recording for the test selection workshop. To summarize, in my experience, test processes intelligence vary widely between teams and companies, much more than the development processes. If you take a step back, independent of which programming language we see teams employ, usually there's an integrated development environment. There's usually a version control system that typically is Git or will be Git in a couple of years. And the different processes look much more alike than the test processes. There's much more variety between test processes. And the analyses I presented today, please understand them as a toolbox. And there are many useful tools in them, but they are not like plug and play, but you have to adapt them and fit them into your processes so that they really work without friction. And it's a good idea to start with an analysis that addresses the pain point that's most pronounced in your environment if you think about using some of these. And typically this takes some deliberation. How much effort would which analysis be? How easy is it to get to run? And if you want to discuss that, I'm very happy. I would be very happy to do that. And just contact me. I'm happy to jump on a virtual coffee call to discuss test intelligence in your environment or experiences we had that I didn't cover in this talk. Thanks a lot for your attention. I think I am at the end of my time box, Reinhard, and I'm looking forward to questions.
Actually, perfect in time. It's just 1 minute left, but we have some questions. So thank you for the talk. Thanks for the insight. The first question is quite simple and easy to answer. Which tool did you use to create the tree maps?
I used our own tool called TeamScale. I try to keep it out of the presentation, but that's the tool I use.
Okay, great. Then there was a question on how to clean up your tests. How do you find out which tests to remove? Because the question was, we usually add more and more tests. Is there a cleanup strategy to get rid of the ones to identify those who are not necessary?
Very good question. And I think one approach would be to compute this curve to see which tests adds how much additional test coverage, and then look at those ones to the right here, because we see that they take a lot of time and hardly add new test finding capability. That doesn't mean you can delete them directly, but I think a good thing would be to look at them and to decide, knowing that they hardly add anything, do I still find anything in this test case that makes it worthwhile keeping? Second answer, I think often it's very hard to decide to delete a test case. So a way around that would be to execute these tests much less frequently, so that you still execute them now and then if somebody's very much against deleting them, and then you don't have the pain of waiting for them much less frequently. Third part of the answer, you can, if you have historic test information, you can also see in the last 5 years when we executed those tests, did they ever find a bug that other tests did not find? And if you see they add hardly any coverage, they didn't find a bug in the last 5 years that we wouldn't have otherwise found, and they take effort to maintain and run, I think that are good arguments to delete them. Thanks for the question.
So basically, you define some parameters for your team and say, if it doesn't work as we expected and it isn't helpful, but uses a lot of time, get rid of it. Great. Okay. And then there's a question, a comparison about the Pareto analysis-based tests compared to impact-based tests, the efficiency.
Was that the question already?
Yeah, it was like impact-based methodology only needs 2% of tests, while others need 11%. So impact-based has clear rationale to test which features, and the Pareto you have, this is more flexible. So what is the efficiency compared with its two strategies?
I think obviously test impact analysis is way more efficient, but there are cases where you can't employ it. For example, if you don't know the code changes. Some of the test teams we work with, they get some of the software they test from other departments or from suppliers, and they don't know the changes in detail. So they can't really look at the changes to select the tests. But Pareto optimization is still applicable in those cases. Another reason might be if it's just one customer we have, they measure test case specific coverage, but they produce very many gigabytes of test coverage information every single day. And they entertain quite an infrastructure to run test impact analysis for them. And there are other customers where they decided maybe it's enough to have the optimization that Pareto optimization provides without the costs of running test impact analysis live. And I hope this answered the question.
I think so. For the last question, I just got someone that says in the chat, thanks, great feedback. That was the question before that. But there's kind of a follow-up question to that. How much it's about the overhead you have, the execution time you need to analyze, to optimize the test, analyze and optimize it. So for Pareto optimization and impact analysis.
There's also, the question makes a lot of sense. And as so often the answer depends. There are some cases, for example, if you have embedded systems and you use hardware profiling, where the hardware profiling interface guarantees you not to have any performance impact. But this is because it has a hardware interface with special pins and a hardware debugger that does that live during the execution, so you don't have any impact. Typically, if we look at Java or C# or SAP ABAP or Python, we have performance impact of 1% up to 10%, depending on the level of instrumentation. But the important message, I think, is for Pareto optimization and test impact analysis, you don't need to measure every single test run, because test coverage is pretty stable across system versions. And so if the performance impact is too high, you just do one measurement test run and then use the coverage you gathered there for the next weeks or months. And then when a lot on the system changed, you do another measurement run. And you can do that at night on a separate system so that the slowdown doesn't impact you.
Okay, thanks a lot. Thanks for the answers. Now we all have time for lunch break. Thanks, Elmar, for being here and for the great talk and for the answers. I think they really appreciate the audience.